we'll take a look at a second example of a problem that requires the use of the Nernst equation. This is going to be a problem that involves something called a concentration cell. In a concentration cell, you have the same materials in the two compartments, right? In this case, Ag and Ag plus in each of the two compartments. And the only difference is the concentration of the aqueous solutions here. So right on the left-hand side, we have a 0.1 molar Ag plus solution, and on the right-hand side of the equation, we have a 1 molar Ag plus solution. Now, this difference in concentration is going to lead to a chemical reaction happening. And let's think about what that reaction would be and how we're able to determine that. Let's think about what nature would tend to here, right? You have a high concentration on the right-hand side, and you have a low concentration on the left-hand side. Now, do we think that things will naturally tend towards a state where the concentrations will become closer together? Will things tend to equalize? Or will the concentrations tend to get further apart from one another? When we talked about spontaneity and entropy, we said that we want to try to distribute mass and energy as evenly as possible. Nature tends towards more even distribution of things. And so it will be more spontaneous for us to try to equalize the concentrations as much as possible. Therefore, in the half cell where the concentration of Ag plus is low, you want to make more Ag plus to raise the concentration. So we'll say we want to raise the concentration of Ag plus here. And so to do that, we have to produce Ag plus, or make Ag plus. Therefore, we would write the reaction in this half cell as one where you put Ag plus on the product side. You're making Ag plus. And the source of Ag plus, that's going to come from the solid piece of silver that's in there. So Ag goes to Ag plus, and then you need an electron to balance this equation. On the right-hand side, we have a high concentration of Ag plus, and so we want to lower the concentration of Ag plus there. Again, the goal is to try to equalize these. So we want to lower the concentration of Ag plus here. To do that, we have to use up or consume Ag plus. And the way that we would represent that in a chemical reaction would be to put Ag plus as a reactant. Ag plus will get converted into Ag solid, and then that removes Ag plus ion from the solution. And we'll put an electron on the left-hand side of that equation to balance the charge there. And so what we've managed to do now is determine what the reactions are that are occurring. We're able to determine that Ag plus is produced in the half cell where the concentration is low, right? Because that helps you to raise the concentration there. We're oxidizing the Ag there, so that's going to be our anode. And we also determined that Ag plus is being used up or consumed in the half cell where the concentration is high. That serves to lower the concentration, again, with the ultimate goal of equalizing concentrations. Since Ag plus is being reduced here, the half cell where the concentration is 1 molar is our cathode. In addition to that, we're asked to determine what the full cell potential is at 298 Kelvin. And so we're going to have to use these two half reactions and use the Nernst equation to get the answer to that. One more piece of information that I'm going to add in here before we go on to doing the calculation is to perform a very careful labeling of these reactions and the concentrations of the Ag plus. So in the anode where we're producing Ag plus, the concentration of Ag plus was initially 0.1 molar. So I'm going to put that it's Ag plus at a 0.1 molar concentration. And in the cathode, where Ag plus is being consumed, when Ag plus is on the left-hand side of the equation, that was initially at a concentration of 1 molar. So I'm going to label that. Labeling that is going to be really helpful as we go through the calculation of the cell potential. I'm going to go ahead and write out my two half reactions here. We had that Ag plus an electron goes to Ag. And again, when Ag plus was on the reactant side, that was at a 1 molar concentration. And we also had the other half reaction, Ag goes to Ag plus an electron. And when Ag plus was on the product side, I'll remind you The concentration of Ag plus was initially 0.1 molar, so I'm going to write that down there. Now, the problem doesn't tell you what the standard reduction potential of Ag plus is, but it doesn't matter what it is. And the reason why is because when you look at these two reactions, one reaction is just the reverse of the other one. I could just tell you that the standard reduction potential of Ag plus is 0.8 volts. And so when you go ahead and look at the oxidation half reaction, it's the exact same reaction, but just reversed. So that's negative 0.80 volts. The standard full cell potential for any concentration cell will always be equal to 0 because you're using the exact same half reaction at the two half cells. The only difference is that one of them has been reversed. And so the standard reduction potential and the standard oxidation potential will be equal and opposite to one another, giving you a full cell potential of 0 for any concentration cell. And so the problem doesn't specify what that is, but it doesn't need to be given to you. It doesn't matter what it is because it wipes out. All right, we can add up the two half reactions, and what we end up getting is Ag plus at a 1 molar concentration plus Ag going to Ag plus Ag plus at a 0.1 molar concentration. This again is where labeling the concentrations is really helpful because it's showing that these Ag pluses are different from one another, and it's also keeping straight which one is which. Because now when we go to solve the Nernst equation and get what the full cell potential is, we'll have that E cell is equal to the standard cell potential of 0 minus R, 8.314 joules per mole per Kelvin, and we were told T was 298 Kelvin, over N. The number of moles of electrons that get transferred here is 1, because that's the coefficient of E minus. So N is equal to 1. And I will remind you that when we use the coefficient, that represents 1 mole of electrons per every mole of chemical reactions. Writing it out like this is not commonly done, but it has to be done here so that you can see how the units cancel out. Faraday's constant, 96,485 coulombs per mole of electrons, times the natural log of Q. Now, the reaction quotient here is going to be product over reactant. And again, because we so carefully labeled these concentrations throughout the problem, we know what the product concentration is and we know what the reactant concentration is. When Ag plus is a product, that's when you're in the half cell that has the 0.1 molar concentration. So 0.1 molar goes on the top. And when Ag plus is a reactant, that was in the half cell where the concentration was 1 molar initially. So 1.0 there. That way, you make sure that you're putting the concentrations in the right place. In terms of the units, the moles of electrons cancel, the mole of reactions cancels, the kelvins cancel, and you're left with joules per coulomb, which is the same thing as volts. And the number that you get for the cell potential comes out to 0.059 volts. And there we have it. It's a relatively small voltage, but it is a significant voltage, right? Because you do have a positive cell potential here, you will have a reaction that will spontaneously occur until the two concentrations equalize one another. And then at that point, you'll end up with a cell potential of 0. The reaction will come to equilibrium. Now, concentration cells have a lot of important applications in, let's say, the areas of biology, in the areas of neuroscience, because almost every cell in our body is a concentration cell of some sort. We have on the opposite sides of the cell of our cell membranes differing concentrations of sodium and potassium ions, and that difference in concentration of the sodium and potassium ions leads to a small voltage. And that voltage can be used for things like nerve signaling. Having a difference in those concentrations can result in an electrical potential being generated that can then provide signals to your muscles to allow them to expand or contract or do all kinds of different things, to send pain signals and all of that. So if it weren't for the fact that a difference in concentration leads to a voltage like this, life as we know it wouldn't exist. So it's interesting to kind of see applications and why this is important and where you would see something like this. All right, we'll take a look at one last example of the Nernst equation before we wrap up chapter 11.